Hi, we're taking a look at reconciling modern machine learning practice and the Bias-Variance Tradeoff. There's this paper on the Internet Archive back in 2019. It's actually pretty recent, and the paper goes into really calling into question this belief of the Bias-Variance Tradeoff, where you test and rather you're training your data and it gets better and better in your training set, but in your test set you tend to overfit and then it gets worse. And what this paper looks at is if you have some capacity, if your network is really complicated, then it does do that. But then once you have overparameterization, it gets better later. So let's implement this using Tensorflow, try it out, and see if we can overcome the bias-variance trade-off. Here I have a Colab notebook hosted by Google on their Colab thing. This is called Reconciling Modern Machine Learning and the Bias-Variance Tradeoff. Just like the title of the paper, I'll put a link in the bottom. You can take a look at it yourself and also run it. So let's expand this and get right into it. First thing I want to do actually is show you that I have this runtime here. Use Python 3 and GPU. I already ran this ahead of time because it takes a long time to run it. Let's just go through the code. So we're challenging this belief of the bias-variance trade-off. If you've taken an introduction to machine learning course, the instructors often talk about make sure that you don't overfit your data. Well, that's exactly what we're going to do, and we're going to show that it works fine so long as you really, really overfit. Okay. This code here, this imports the MNIST data set. The MNIST is what we're going to work on because it's easy and fast. It's already preloaded in TensorFlow. And just some imports here. We're also going to create a validation set and consistently create that validation set. We could use TensorFlow to say, hey, peel off a bit of the data for a validation set, but this way it's repeatable. It's always the same. All right, so we have 59,000 items in our training set, 1,000 in validation, 10,000 in our test set, and our training set has a minimum and maximum value of 1 and 0. So it's fairly normalized. If you're not familiar with MNIST, it's handwritten digits. The data in question is not really important. What we're going to do is just overfit data and show that it works. This is just a helper function to show how many layers our network has, how many free parameters it has. So let's take a look at this network and how we're going to make it. We're going to make a ResNet-like dense network. So these are handwritten digits. They're images of handwritten digits. And with images, we should probably use something like convolution. But for the sake of this demo, we're just going to use dense. And we're going to do it in a ResNet-like way. So our output is going to be, for example, if we have two fully connected dense network layers, we're going to do two, we're going to have the input, we're going to wrap it around with two dense layers, and then we're going to add the input to that. That's going to be the output. That's kind of what the ResNet is. Without ResNet, our output with two layers of fully connected layers would just be like our input wrapped in two dense layers. Here's the code of the of my implementation of a dense ResNet-like layer. We can tell how many filters that we want. So in this case, that's going to be, how many items are in the dense layer, what our activation function is, and kernel initialization, and how many layers that we want. So by default, we just put 2, but we could do more than 2, or we could just say 1, and it doesn't have multiple layers. All right, so we're going to create a function to run the experiment, and here it is. So we can run different experiments, and we can tell it how many ResNet blocks we want. So the basic network takes the data in, runs it through one dense layer, and then does all the blocks. So we could have multiple ResNet blocks, and then in each block we could have multiple layers in that block. So how many dense layers do we have in each block? And then how many filters do we have per block? And then we have all of these other settings. How many epochs we're going to train, the activation function, the optimizer, the initializer, and whether or not we're going to use distortions. Okay, so this is the code here. You can walk through it. I'm not going to walk through all this code. The objective of this is not really to talk about the structure of neural nets. It's about this bias-variance trade-off. But basically, this model can be summarized as follows. We have our input. We flatten it. It goes through a dense layer. And then it goes through our dense ResNet layer, given the number of layers and filters that we specified, and then a number of those ResNet blocks that we specified. So if we had 10 ResNet blocks, we would repeat this 10 times. And if each of those blocks we had 5 layers, then we'd have 5 layers in each block, and then for each of those we'd have that many filters. Maybe it's like 50 filters per that. So that adds up quite a bit. And then after all of that, so that gets repeated, we do one more dense layer, and then our final output. Okay, so here's our experiments. Let's just start really simple network. We're going to just see if everything works. We're going to set the number of ResNet blocks to 0. All right, so if we take a look at this area here, we are just going to 0 out. Right? We're going to multiply. We're going to repeat that 0 times. So it's going to be our dense layer, this dense layer, this dense layer, and then the output. And we run that, and we can see that we get 95% accuracy. Not too bad for just taking an image, flattening it, and doing a dense layer on it. So the idea here with the bias-variance trade-off is, and the theory is, if you have too many free parameters for your model, it can just memorize your training set and not actually do well on test. So let's start adding some more free parameters and see how well it does. We're going to do it with one block here. So dense, our ResNet block, another dense. And the ResNet block just has 2 layers in it. And so you can see that it's a dense, and then in the ResNet block, there's 2 dense layers, and then all of that. So before I got 95%, and when we have this one ResNet block, it got 95% again. So free parameters, right? Free parameters is how the system could memorize all of the data. Remember, the training set is 59,000 images, and each image has 784 pixels in it. So if we had that many free parameters, it might be able to just memorize all of the data. How many free parameters is that? I actually didn't calculate that before this video. I probably should have. So if we had, 46 million free parameters, we'd be able to just totally memorize every single pixel for every image for the training set and completely fail the test set. So we'll climb our way up to that. So here we only have 42,000. And then once we have this extra block, we're only at 47,000 free parameters. So let's get large and stupidly overfit. Here's a ridiculously large network. What we're going to do is we're going to have 102 dense layers with 200 filters per layer for a total of 4 million parameters. That's a lot of parameters for such a trivial data set as MNIST. And how that's set up is we have our input and then 200 dense filters and then 10 ResNet layers with each having, 10 ResNet blocks, each having 10 layers. So that's 100 layers right there. And then for each of those, there's 200 filters. And then it goes to 1 dense and the output. So here's the results. It ran, how long did this take? It took 200 seconds and 96% accuracy, which is really nice to see that this 96% accuracy on the test set is very much in line with the validation set and not too far off from what the training set was. So that's really nice. And it didn't overfit. So, and it trained. It's, 102 layers. Okay, so let's get even more stupidly overfit. 200 layers, 200 filters per layer. Isn't enough for you? Okay, it seemed like rookie numbers. Let's crank that up. So let's do 102 dense layers with 500 filters for a total of 25 million free parameters. This is way more than enough to memorize. And if we take a look at this paper, what we're doing by making this particular network here, which is just ridiculously large and has a ridiculous number of parameters, and it's ResNet, so the information can flow through the network from the front to the back pretty easily. It's not like there's a lot of hidden information in the network. It's not like there's like some massive bottleneck somewhere. We're really making a network that has a capacity that's like way out here compared to the amount of data that we have. So we should be way out in this regime. All right, so 25 million parameters. Again, 102 layers with 500 filters. And there we go. Look, we got 96% validation, 96% on the test, and the training set wasn't too far off. So yeah, this was a great paper to help us break out of this misinformation that that you need to reduce the number of parameters in your model for fear of overfitting. And if you go into over parameterization in a very strong way and have a reasonable network, then you can get into this modern and interpolating regime, and your test risk, your test set, this risk here is your error, is what they're talking about, can keep going down, and you don't have the problem of the over parameterization. So there you go. Hope you enjoyed it. I'll put the links below, and I hope to see you in the next video.